Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we want to talk about the relationship between force and momentum. So what is a force? I think we all learned in junior school. A force is a push or a pull. Let's take a rubber band as an example of a force. Here's a piece of cardboard, here's a rubber band. If I let the piece of cardboard go, off it disappears. The force pulled the piece of cardboard in that direction. So we can actually represent force by means of an arrow. There's the piece of cardboard, and that arrow is acting on the piece of cardboard. The magnitude of the pull is the length of the arrow. The head of the arrow is the direction that the elastic pulled, and the cardboard is the object that it's pulling on, and the base of the vector arrow sits on the object which is being pulled. But now, what is meant by, so this would be a force. What is meant by a force net, or a net force? Sometimes represented F net. Okay, let's take this as an example. Here we have a ring. It's being pulled by many forces or elastics, all equivalent elastics. You'll notice that this washer is not moving. Forces are balanced. There's no net force. We could actually, if we wanted to prove this, we could use vector addition of all these various forces. For example, let's start with this force. It's in that direction, pulling on the washer. That one is pulling in that direction, and when we vector add, we add the head to the tail. So this one will be in that direction. That 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 one will be in that direction. And that one will be in that direction. There's where we started, and there's where we end. If when we add all the forces and we come back to where we started, we have what is called a net force of 0. There is no net force. However, what if I were to pull that up? These arrows would get longer, those ones would get shorter. And if we had to repeat the same process, and notice what's happening to this washer. The washer wants to go in the direction of the net force, which would be in that direction. Let's just suppose we were to now draw a force diagram showing all those forces. We would have to have, and let's start again with that force. Fairly long, add it to this one, in that direction, add it to a fairly short one up, fairly short one in that direction, this one getting quite long, this one getting even longer, and now we see that there is where we start, there is where we end, and our resultant vector would be this vector here. That would be our resultant. That's when we add all those vectors together, we get this washer wanting to go in that direction. And that is, in fact, what we mean by a net force. There is now all the forces, when added up, vector addition, there is a remainder, and that remainder is the net force. Now, let's go to our best physics friend. We're going to find two formulae on our data sheet that talk about force, in fact net force. And here is the one. Force net equals ma. That is Newton's second law. Force net equals ma. But there's another force equation which says this. Force net equals delta P upon delta T. Let's just take our best physics friend, which is the data sheet, and these two formulae. They seem to be saying the same thing. This is Newton's second law, but could this also be Newton's second law? They're both talking about a force acting on a mass, in this case causing an acceleration. The net force is equal to the product of mass and acceleration. Here we have one object spoken about, and here we have a net force is equal to change of momentum upon change of time. Now, just as a matter of interest, for our better students, whenever you see delta T as a denominator, meaning on the bottom, we always in science talk about rate of something. In this case, the rate of change of momentum. That means rate when it's a denominator, delta T, of momentum. But let's try and show you that in fact both of those force nets are identical. Let's do it as follows. Let's take this. Force net is equal to mass times acceleration. But acceleration, what is acceleration? It's change of velocity over time. So that is equal to mass times change of velocity over change of time. But what is change of velocity? Change of velocity is always, change of anything is final minus initial. So change of velocity is V final minus V initial over change of time. But what is this also equal to? If we get rid of the brackets, we could say that mass times V final, and then getting rid of the brackets, mass times minus mass times V initial over change of time. But what is this equal to? We should remember that as being equal to change of momentum. So that, from what we've looked at earlier, this is simply the formula for change of momentum. In other words, this is equal to delta P upon delta T, which is that. So we've gone from that to that. Let's just briefly recap how we did it. According to Newton's second law, force net is equal to mass times acceleration. Acceleration is change of velocity over change of time. Change of velocity is final velocity minus initial velocity, all multiplied by mass. Getting rid of the brackets, mass times final velocity minus mass times initial velocity, and that's gotten rid of the brackets. But that is otherwise known as change of momentum. And there it was all over change of time. So we've now proved that Newton 2 is the same as force net equals rate of change of momentum. So the two formulae are almost identical. We're always assuming that our mass is not changing. And we are told that this is the general form of Newton 2, and this is the special case of Newton 2.